All right, folks, so let's take a look at our first integral by trig substitution. I'm going to say that again so you can label your notes. Integration by trig substitution. Now, on this problem here, our first step is going to be to label our triangle. And you can go back to the previous video, but I'm not going to spend too much time on that. That's going to be a 2 here, square root of 4 minus 9. X squared, and this one here is going to be a 3x. And our goal for this is going to be to substitute trigonometry equations into our integral. And to do that, we have to get a match. And I'll explain what I mean by that in a second. First thing we're going to do is we're going to solve for x, and I'll explain why. The reason why is we want to get a match with dx, and if I solve for x, and then I take the derivative, I will have a dx and I'll have a match. Let's do it. So to solve for x, I'm going to go ahead and I'm going to write a trig equation that has an x in it and a number. So I'm going to choose these two sides right here. You always want to choose the one with an x and then the one with just a plain number. So this is going to be sine of theta is equal to opposite over hypotenuse is 3x over 2. That's actually going to be a really useful equation later, so we do want to keep that. We also want to solve for x, so I know that I can multiply by 2 over 3 on both sides. You can see here the 2 cancels with the 2, the 3 cancels with the 3, and I do get an x is equal to 2/3 sine theta. Next step is going to be to take the derivative of both sides, and we're taking it with respect to the variable that exists on both sides. In this case, we'll have 2/3 cosine theta, and then I have a d theta. It's because I'm taking the derivative with respect to theta. It's almost like the chain rule, taking the derivative of the inside. Now on the right side, we're taking the derivative with respect to x. So the derivative of x is a 1, and then I also have to put my dx. And I can simply write that as just dx. And you can see now I have a match for my dx right here, which I'll soon substitute in right here. All right, the next thing that we're going to do is get a match with the square root, now that we already have a match with my dx. So now I want to get a match with this. And to do that, I'm going to choose the two sides that have just a number and the square root. And that's going to be my adjacent and my hypotenuse, so that is going to be cosine. So I'm going to get cosine of theta equals the adjacent, which is 4 minus 9x squared under the square root, over my hypotenuse, which is 2. All right, multiplying by 2 on both sides, I get a 2 cosine theta is equal to the square root of 4 minus 9x squared. And that's going to be really helpful, this one right here, because you can see I have a perfect match with that. All right, I keep talking about these matches, and what I mean is we're going to substitute now into the things that we have for a match. So I'm going to have the integral of 1, that's going to come from right here. And now instead of writing the square root here, I know that the square root is equal to 2 cosine theta. Now I also have to substitute in for my dx, and my dx is this, a 2/3 cosine theta d theta. And it's kind of nice here because you can see my 2 cancels with my 2, my cosine cancels with my cosine, and I'm actually just left with the integral of 1 d theta. And don't forget as well, folks, we do have a 3, and it's a divide by 3, so that's going to be a 1/3 out in front. Now integrating the 1/3, the integral of 1 d theta, well, that's going to be equal to 1/3 theta plus c. Just think about if this was a 1 dx, we know that that would be an x. Now folks, you might say, we're done, we integrated. However, when we take the integral of a function that has an x in it, our answer better have an x in it, and it does not in this case. So what I'm going to do is I'm actually going to return to this equation right here, and I'm going to solve for theta. Actually, is there a better one there? Yeah, actually, you know what? The better one would be kind of our original here. That one right there. So let's actually use that one. And it doesn't matter which one you use, but this one's going to be a lot easier. So I'm going to take this one right there. I'm going to solve for theta. So I'm going to take sine inverse of both sides. Okay, my sine inverses and my sine cancel, and I'm left with a theta is equal to sine inverse of 3x over 2. And I could have gotten that from the one I originally highlighted, but it would have been a bit more work. All right, folks, so now we are done once we substitute in. So I'm going to write my 1/3. Now instead of theta, I'm going to substitute in this trig function here. And now I am done. So it makes total sense why we call this integration by trig substitution, because we are substituting in a bunch of trig functions into our integral. All right, let's try another one. Now on this particular problem, you've probably never seen a dx up in the numerator, and that might freak you out. But don't be too worried. What I'm going to ask you to do here is think about rewriting this as the integral of 1 over the square root of 49x squared minus 16, and then you'd have dx on the outside. And it's fine if you rewrite it like this. I might actually just use this one, but I did want you to see that that's nothing special. It's nothing crazy different than what we've been doing. All right, so filling in our triangle here, and we are experts at this, so I'm not going to spend much time on it for sake of time. But our hypotenuse is a 7x, and we'd have a side length of 4, or a leg of 4. And then we've got the square root of 49x squared minus 16. All right, we're going to try to get a match with the dx, and I'm going to just use the original. I just wanted to show you that that looked like something that we had done before. And to solve for dx, I need to first solve for x and then take the derivative. So to do that, I'm going to set up a trig function with the 7x and the 4. And we can try to do this with cosine because there's an adjacent in the hypotenuse, but let me show you what happens. We get cosine of theta equals adjacent, which is 4 over 7x. Then we multiply by 7x. And we get 7x cosine theta equals 4, and that's it. Now, if I take the derivative of this, this is product rule, and this is going to be really messy. So when a situation like this happens, it's a sign that you need to switch these two. Like, you need to take the reciprocal. And to do that, instead of using cosine, we're going to take the reciprocal of cosine. We're actually going to use secant. And you'll see why this is going to be so much better. So secant is hypotenuse over adjacent. Here we're just going to multiply by 4. Now we get 4 secant theta equals 7x. Divide by 7. That's going to give me a 4/7 secant theta is equal to x. Now taking the derivative of that, I get a dx equals 4/7, and we should know that the derivative of secant is secant theta, tangent theta, d theta, and that's from our SST. All right, so that's going to be super useful. We have a match with the dx right here. All right, next thing we're going to do is we are going to create an equation with the square root. And we're going to choose just the number. Now, this is almost always almost always the case where we want to kind of use a function that's already in here. So in this case, I've got an opposite and an adjacent. So I'm going to choose tangent because at some point it might cancel. So I'm going to have tangent of theta equals opposite over adjacent. And now I'm going to solve for that square root. So to do that, I just multiply by 4. And that's going to give me a 4 tan theta is equal, and this cancels, to my square root of 49x squared minus 16. And I'm happy. And I box that off. It's not my answer, but I box it off because, look, I have a match. And that match is that square root right here. So now once we've matched both of our dx with our square root, we're going to go ahead and substitute in. So we're going to get the integral. The dx is secant theta tan theta, and I can go ahead and put that d theta out here. So I just put in the dx. And now in the denominator, I'm going to put in the square root, which in this case is a 4 tangent of theta. All right. I just noticed here that I forgot to put in my 4/7 for my dx, for my d theta and dx there, so I should have a 4/7 here. I forgot to put that in. No big deal. All right, next thing I'm going to do is I'm going to pull out the numbers. In this case, it's going to be a 4/7 and a 1/4. And then my tangents are going to cancel. So I've taken care of my numbers. I've pulled those out. My tangents have canceled. I'm just left with a secant theta, d theta. Now multiplying, this is going to give me a 4/28, the integral of secant theta. And you might be thinking, do I know that one? And you actually don't. I'll tell you what it is in a second. First of all, let's go ahead and put that 4/28, which I can reduce to 1/7 because I'm dividing both of those by 7. All right, so that gives me 1/28. Now here's something I would tell you. You don't have to memorize this. I would tell you on a test what that is. The integral of a secant theta is ln secant theta plus tan theta. See, we've never seen that before. All right, at this point right here, we now need to substitute in so that we have an answer in terms of x, and it's a lot easier than you think. So I'm just going to rewrite this as 1/28 ln, and now I need to see, is there somewhere in this problem where I solve for secant theta? Yeah, there is. Your very first step right here, I had that secant theta was 7x/4. So I already have secant theta here, so I'm going to substitute that as 7x/4. Now my tangent theta, I do have that somewhere, right? That was from the very start here, that tangent theta is equal to this right here. So I already know what tangent theta is, so I'm going to plug that in. And I know it's really tempting sometimes to think that you could cancel one of these with one of these numbers, but because of that natural log there, we cannot do that. So don't forget my plus c, and we are done. Folks, we will get lots of practice with this. It is a challenging topic, but let's just practice and see where we can get on the first day, and we'll try to get it down by the second day. Thanks for watching.